Okay, so moving forward, potential energy is the stored energy, so that's gonna depend on the position of an object. The larger the height is, the larger the potential energy is gonna be. Okay, so let's take a look at the potential energy of the weight set that this guy is lifting and compare it to the potential energy of the people that Anderson is lifting. Alexa versus Anderson. So which one is gonna have more potential energy? Which one is gonna have more stored energy? The weight set or the people? All right, so that one is gonna be the next problem. Okay, so what I'm going to do is I'm just going to cheat a little bit. Okay, so we got the numbers from here, so I'm just going to grab these numbers. Okay, so I don't have to worry about the conversions. Okay, so we got one set of numbers here. All right, so let's get the numbers for. Okay, so I got the next set of numbers here. Okay, so we're going to be looking at the potential energy of both of them. All right, so question mark in terms of joules and expressing in terms of calories. Okay, guys, just remember the statement that I made here. I said the amount of force that these two are applying is going to match the weight of the object these guys are lifting. Okay, which means that they're lifting at a constant speed. Okay, so if you think about it, now look at the net force on the y direction. Okay, so this one is the applied force in the upward direction. W is in the downward direction. They're applying a force on it, but they're lifting at a constant speed, so there's no change in acceleration. So which means that the net force is the same as the weight. Weight is going to be the same as mg, so that's what we got. Okay, so now let's write out the equation for the potential energy. Potential energy is the same as mg times the height. Okay, do you guys notice that this mg is the same as the weight? And which happens to be the same as the applied force? All right, and so okay, so let me just box this successfully. It's gonna be mg times the height. And then I want you to take a look at this equation now. Take a look at the amount of work done. Here's the applied force. Here's the applied force. Applied force causing displacement. Applied force, if you apply the force at a constant speed, the applied force is going to be the same as the weight of an object. So this applied force is the same as mg, right? So this is the amount of work that you do, and this is the amount of energy that you transfer. Notice that at the end, it's going to give you the same numbers. Okay, so it works out just so that you end up getting the same numbers. The reason why that happens is because the amount of work that you do is the same as the amount of energy that you transfer. So you end up transferring the same amount of energy to the objects that you're lifting. All right, so which means that this is the potential energy of the weight set, and this is the potential energy of the people. All right, so the amount of work that you do in lifting something up is the same as the amount of energy that you transfer to the objects that you're lifting. All right, so they, all of a sudden it fits the definition. Applied force, when you apply the force at a constant speed, the force is going to match the weight. So the applied force becomes the weight, so which means that the amount of work that you do is the same as the amount of energy that you transfer to the objects that you're lifting. Okay, so here's the weird stuff. I'll take a look at this guy. He's breaking the world record in 1976 by lifting something almost 600 pounds over 6 feet. But notice that this guy's pudgy. I mean, these guys, most athletes look like athletes, and then these heavyweight lifters, they kind of look like couch potatoes, most of them. I mean, obviously the guy's extremely strong, but if you're in an elevator with this guy, if you were to say, hey, I'm an Olympic athlete, you're thinking not really. Okay, I mean, he doesn't look impressive. You would expect him to be really muscular, but he's pudgy. Why is it that these guys are pudgy? This is what I'm talking about. 1976, this guy's breaking the world record, and guess who Mr. Universe is 1976? Arnold Schwarzenegger. Look at Arnold Schwarzenegger. Guys, look at the muscles. Look at his biceps. Arnold Schwarzenegger's biceps are thicker than this guy's thigh muscles back then. And he's not even flexing his muscles. More than likely, this is his driver's license picture. All right. So you're looking at these two guys, and the question is, which one is stronger? Is it Arnold Schwarzenegger or is this guy? What do you guys think? Clearly, Arnold Schwarzenegger looks impressive, right? So the question is, which guy is stronger? The guy on the left, who looks pudgy. I mean, obviously, this guy is muscular. He's got muscles under the fat layer of fat, but damn, his muscles are not as big as Arnold Schwarzenegger's muscles. And Arnold Schwarzenegger is probably about the same height, possibly taller than this guy. So who's stronger? What do you guys think?
My money's on the guy on the left.
Okay, okay, I need a justification.
So we were just talking about like potential energy.
Yeah.
And I see a bunch of stored calories, which can be used to transfer, energy to something else.
Okay.
There's a saying in weightlifting and that culture, just mass moves mass. So the guy on the left is most likely heavier. So he has probably more inertia and potential energy.
Okay, I'm gonna both of you guys. I'm gonna give you 5 points, despite the fact that your arguments didn't really go anywhere. But it's a good start. The guy on the left is probably not as heavy as Arnold Schwarzenegger was at the time. Okay, it's probably, I would say he's maybe the same weight, probably weighs less. Arnold Schwarzenegger in his prime, this guy was, he was a monster. This guy was really, really beefed up in his prime. I mean, he was the Mr. Universe, guys. These guys tend to get really, really big. All right, so Arnold Schwarzenegger was actually heavier than this guy in his prime, I believe. I mean, if they're the same height, I would say Arnold Schwarzenegger was heavier. Muscles weigh a lot more than the fat does. Okay, so let me talk to the biology majors, because I know that some of you guys are getting into biology or something related to biology. Okay, in terms of strength, what matters? Is it the size of the muscles? Or is it the muscle fiber density? Okay, guys, you get your strength from your muscle fiber density. Yeah, bigger the muscles are, stronger you will become, but the determining factor is your muscle fiber density that you're looking at. The guy on the left, some people are born with it. It's got a much larger muscle fiber density, and when the muscles become bigger, the muscle fiber density goes down. All right, these guys are naturally stronger. I mean, this guy is breaking the world record in 1976. There's no question that this guy is stronger than Arnold Schwarzenegger. And there's absolutely no question that Arnold Schwarzenegger is going to be much stronger than I am, because he's got bigger muscles. I mean, his prime, he could freaking kill me. There's no question. Bigger the muscles are, stronger they will be. They're not going to be as strong as these people are. These guys are animals. Okay. Their muscles are not as big, but they're just big enough. It's the muscle fiber density is what matters in this case. These people have the right amount of density. If you make the muscles any bigger, their muscle fiber density goes down. They're not as strong. And obviously, this guy is trying to qualify for heavyweight, because that's when he wants to make the biggest impact. So there are two ways you're going to get up to that level. Either make the muscles bigger, but it's going to happen at the expense of strength, so he doesn't want to do that. The second way of doing it is just have the most delicious diet that you can imagine. Okay, just eat the wrong stuff, just get fat. All right, so that's what they go for. All right, so Arnold Schwarzenegger, though his muscles are bigger, is not as strong, because he probably doesn't have the same fiber density in the first place. Okay, this guy's a bodybuilder, this guy's a powerlifter, so it's not the same. All right, another thing that I want you to notice is this guy's breaking the world record, right? A single lift. What is the amount of energy that he had to expend? The amount of energy that he ended up putting out is like 1.22 calories. It cost him literally 1.22 calories of work. This is the amount of energy that he lost in lifting this up. 1.22 calories of work. Imagine that this is happening in the middle of, or towards the end of Cold War. Middle of it is more like it. And this guy's the Russian bear. He's trying to impress the world, right? So he lifts one time, and he said, okay, this is the world record. In order to impress everyone, he lifts it 99 more times within an hour. So how many calories did he burn in lifting it 100 times within an hour? It's going to be 122 calories. That's the amount of work that he would have done. If he wanted to impress us, he would just keep lifting it like 100 times within an hour. He would have burned like 122 calories. Now he's feeling hungry. Guys, one rich cookie, how many calories? A lot more than 122 calories. So powerlifting, you don't burn a lot of calories, basically. All right. So if you want to gain weight, you can literally gain weight easily by doing powerlifting. Okay. This is bodybuilding. They're not the same thing. All right. Blah, blah, blah. All right. Kinetic energy. Kinetic energy is the energy of motion. Notice that the car is speeding up. from 20 meters to 3 meters per second, 20 meters per second, 30 meters per second. So here's a question for it. Is there work being done on this car? How would you answer it? Is there work being done on this car? All right, the answer that I'm looking for is, of course, the work is being done on this car. How do we know? Number one, the car is speeding up, which means that the car is accelerating in the forward direction. Acceleration is caused by a force. So the force is going to be in the same direction as the motion, right? So motion is in the forward direction, the force is in the forward direction. So which means that positive work is being done on the car, which means that the energy is being transferred to the car. Notice that by just looking at this, I just visualize everything. This thing is speeding up because there's a force acting on the car. How do we know? How do we know that there's a force acting on the car? We know that there's a force acting on the car because the car is accelerating in the direction of the force. Motion is in the direction of the force, which means that there's work being done on the car. The work is positive. The car is getting energy. And the car is getting energy in the form of kinetic energy. Kinetic energy is the energy of motion. It's going to be related to speed. All right, so kinetic energy is the energy of motion. All right, here's your mass. It's moving. By virtue of its motion, it's going to have kinetic energy. So kinetic energy depends on your mass and depends on the speed. Square the speed, everything is divided by 2. That's it. All right, so that's your kinetic energy formula. All right, K is your kinetic energy. M is your mass. V is your speed. Speed is meters per second. Mass is kilograms. Energy is in terms of joules. Kinetic energy is going to be related to speed. Kinetic energy is going to be related to speed. Okay, so when I drop the ball, what happens? Accelerates, right? So what that means is the kinetic energy of the ball is going to go up. So the faster the ball moves, the larger the kinetic energy is. The slower it moves, the smaller the kinetic energy is. So kinetic energy is going to be directly proportional to the speed. Faster it moves, larger the kinetic energy is. Slower it moves, smaller the kinetic energy is. Kinetic energy is proportional to speed. Potential energy is proportional to height. It's going to be proportional to height. Kinetic energy is proportional to speed. And then we got mechanical energy. All right, we got the best answer to put in the chat. All right, so we didn't talk about conservative force field, but you can kind of guess what the answer is. Okay, very good. A is the best answer, right? Energy related to position is potential energy. Give yourself 5 points for that one. Okay, so energy related to motion is kinetic energy. Very good. Give yourself 5 points for that one. Okay, so let's do this. Mechanical energy. All right, mechanical energy is a combination of kinetic and potential energies. All right, so that's the next topic.